Up to this point, we've been talking about the derivative as representing either the slope of a curve at a point or the instantaneous rate of change of some quantity over time. However, from our notation of taking a function f of x and writing its derivative as f prime of x, you might realize here that the derivative of a function is in fact a brand new function. And so anything we can do with the original function, we should be able to do with this new function. For instance, we can differentiate it. We could take this function here, differentiate it with respect to x, and get a whole new derivative. We call that derivative the second derivative of the function, and we denote it by putting 2 primes instead of the single prime that we have for the original derivative. And sometimes when we're talking about second derivatives and so on, we will sometimes refer to as the regular derivative as the first derivative, just to avoid any sort of confusion from just saying derivative. There's also no reason we have to stop there. We can take the derivative of the second derivative. And it really shouldn't be too much of a surprise that we call this the third derivative, and we put 3 primes. We can also keep going. We can take the derivative of the third derivative. At this point, just putting primes like we're doing here gets a little bit unwieldy, so we like to switch to instead using a number. What we do is we still write the f of x, and instead of the primes, we put the number of derivatives in parentheses, kind of as an exponent, but not as an exponent. The parentheses here are part of the notation, trying to say that this is a derivative and not some sort of exponent. In general, we have the higher order derivatives. Which derivative we're talking about here is called the order. So the first derivative is order 1, second derivative is order 2, and so on and so forth. So if we're talking about order n, or nth order derivatives, we put f to the parentheses n derivative of x. And we can do this for any positive integer n. Now, we do also have another notation for derivatives. Remember, we have the dy dx notation. And we will actually go ahead and use that notation as well for the higher order derivatives. For the second derivative, we can write this in 2 different ways. We can write that as so if we have f of x and we don't want to write f prime of x and put the derivative thing in front of that, we instead are putting basically 2 derivative things in front and basically combining them together and putting a square on the d and the dx. And we also frequently will write this as d squared y over dx squared. Note here that the square on the d is on the top is on the d, on the bottom is on the dx. But the point here is that d squared dx squared is the same as we have over here. It's just instead of putting the y behind the fraction, we're putting it on the top of the fraction. We can do exactly the same thing with the other ones. We can write the triple derivative, the third derivative, as d cubed dx cubed f of x, or we can write it as d cubed y over dx cubed. Now that's not really a cube. I'm just saying that just because we're writing it as a kind of an exponent. And then we just have the same thing on these. Now, actually taking these derivatives does not really require any brand new techniques. We basically are just repeating what we were doing before. So, for instance, let's take problem 14. Here they give us a function f of x. It's going to be x to the 4th minus 2x cubed. And what they're asking us for here is the third derivative of this function. Now, we're not going straight to the third derivative. What we're going to do is we're going to differentiate this 3 times. First, we'll find the first derivative. Of course, we know how to do that by this point. When we differentiate x to the fourth, we take that power of 4, we put it out in front, and then we lower the power of 4 to a 3. And then here, we take the 3 for our power here, bring it out in front. 2 times 3 gives us a 6, and then we lower the 3 to a 2. Now we move on to the second derivative. We differentiate this a second time. We bring down that 3. So 4 times the 3 gives us a 12. And now the power of 3 gets changed to a 2. Here, the 2 comes down. 6 times 2 gives us a 12, another 12. And then 2 lowers down to a 1, or just x. Finally, we take the third derivative. Just differentiate what we have here again. So we take down that 2. 12 times 2 gives us 24. We're just left with an x there. And then here, the x becomes a 1, so we just get a minus 12. That is the third derivative of this function up here. Let's look at problem 11. Kind of going backwards, but there's a reason why I did this one first. It's a little bit easier. A function f of x is equal to x plus 1 over x minus 1. This time we're not asked for the third derivative, we're just asked for the second derivative. But it is a fraction, so we're going to have to do a little bit more work in order to actually find the derivative. For instance, right away, you might think, well, let's use the quotient rule. When we need to differentiate this and get the first derivative before we can get the second derivative, we use the quotient rule on this. Remember how the quotient rule goes. We take the derivative of the top. Derivative of x plus 1 is just 1. We take that times the bottom, which is x minus 1. Then we subtract, because we're differentiating the bottom this time. But we're going to leave the top alone. And the derivative of the bottom, the x minus 1, is a 1. Finally, all that's over x minus 1 squared. We'd square that bottom. Now, if we're just looking for the first derivative, we could just leave it the way it is. But since we want to differentiate this again, it would be nice to have it written in a slightly nicer form. So we can actually get to the... So we can actually do the derivative real easily. So I'm going to simplify the top. It's actually not too bad here, because the times 1s don't really matter. We're just taking x minus 1 minus x, and remember to distribute that negative, so we have a minus 1 as well. So we have an x minus an x. Those actually cancel each other out. But then we have a minus 1 minus 1. So we end up with a negative 2 over x minus 1 squared. And now this is the function we want to differentiate to get the second derivative. And you could actually use the quotient rule again if you wanted to. I think in this particular case, it'd be easier to use the chain rule. If we interpret the 2 down here as basically meaning a minus 2 power on x minus 1, we can interpret this as negative 2 times x minus 1 to the negative 2 power. And now we use the chain rule, or you could say, if you want to call it that, the general power rule. And that's what I'm going to use here. We differentiate this thing. We still have the minus 2 that was sitting out in front. But now we take this minus 2 and we move it out in front. We have the x minus 1 to 1 less power. So minus 2 minus 1 is a negative 3. And finally, remember because of the chain rule, we had to multiply it by the derivative of what's inside. Derivative of x minus 1, well, that is just a 1. So that's actually pretty simple in this case. So what do we have? We have a minus 2, a minus 2. Those combine to be a positive 4. We still have the x minus 1 to the negative 3, and then the times 1 doesn't really matter. And if you really want to, we can interpret the minus 3 power as a cube on the bottom. So we can interpret this as 4 over x minus 1 cubed. And that is the second derivative of x plus 1 over x minus 1. So why do we care about higher derivatives? Is it just something that we can do because we saw the derivative is a function itself, so we might as well go ahead and differentiate just to see what can happen? Well, I claim that the idea of the second derivative is actually something you have seen before. Remember when we talked about speed and velocity? We had, or s of t, this is our distance function. It's representing the distance some object has traveled over time. T here is representing time. Its derivative is, we could say it's the speed or velocity. Now the difference here, speed is usually treated as a positive value. Velocity has sort of a direction to it. Really, when we're talking about just moving along a line or a curve, that just means do you go forward or backwards. Velocity could have a negative to it. So I'm going to go ahead and stick with velocity. It's usually what we use when we actually talking about derivatives. But the question here is, what if we take the second derivative? What is the second derivative of distance, or in fact the derivative of the velocity? Remember, the derivative is a rate of change. We're actually asking, how quickly is the speed changing? How quickly is this velocity changing over time? And we have a term for that you've probably heard of before. It's called the acceleration. If you accelerate, then you are changing your velocity, you're changing your speed. And it's a measurement of how much you're changing that speed. Now, usually we won't need to go past the second derivative. In general, the second derivative is probably the cap on how much you really ever need to take derivatives, at least until you get to things like Taylor's theorem and stuff like that. We will see the second derivative come up a decent amount in Chapter 3. We're going to be using that to help us solve some problems. But there's no reason we couldn't look at the third derivative if we wanted to. In fact, the third derivative can be pretty relevant in this particular context. When it comes to the distance function, velocity, and acceleration, the third derivative measures how quickly the acceleration changes. If the acceleration changes too rapidly if you're in a vehicle, it can be rather jarring. And so sometimes in certain cases, like if you're designing stuff like a road or an elevator, you might have to take this into account because you don't want your passengers to deal with that kind of what we call a jerk. To use a kind of a, it sounds like a really not very precise term, but that's what they use in engineering and physics sometimes to describe this particular quantity. But those are cases where those kind of things can be brought up. But let's actually put this into practice. Let's work out a problem. Let's look at problem 35. Let me just read that straight from the book. A ball is propelled straight upward from ground level with an initial velocity of 144 feet per second. And then there's 4 parts to this problem. I'll read those as we get to them. But let's kind of get an idea of what we're talking about. We've down here on the ground, we have a ball that's launched up into the air. We're kind of just assuming it's straight up. We're not worried about any horizontal velocity or anything like that. And its initial velocity, right when we launch it, is 144 feet per second. We want to find the position and the position function and all that for this situation. And we kind of have to figure out what would be the formula for such a thing. Notice that once we've launched the ball, the only force that's acting on the ball is just gravity. We're ignoring any sort of wind or air resistance. We're working with a very simplified situation here. And it'd be definitely possible to include those, but we're not going to touch that right now. From physics, we have an equation. F equals ma. F is force, m is mass, and a is acceleration. The only force here being gravity means that the F here is going to be constant. We're assuming that it doesn't go too far compared to the size of the Earth, and so the force is essentially just a constant value. We're also assuming that the ball doesn't change. Doesn't lose piece of itself as it's going, so the mass is going to stay the same. And that means that the acceleration is constant. When the acceleration is constant in all those kind of situations, the distance function always has a specific type of form. You have s of t is equal to 1/2 a, the a being the acceleration, times t squared, plus v naught, putting v with a little zero below it, times t, plus s naught. I'll talk about what v naught and s naught are in a moment. But essentially what we have here is a quadratic. We always get a quadratic when we're dealing with constant acceleration. We will discuss exactly why that always happens in a later chapter. But the point here is that once we have this quadratic, we can easily differentiate it to get the velocity and acceleration. When we differentiate it one time, well, we're differentiating with respect to t here, so t squared becomes a 2t. The 2 will actually cancel out the 1/2, so we'll get a times t. This t becomes a 1, so we get a plus v naught. And then the s naught here is being treated as a constant, so it goes away. When we take the second derivative, we differentiate at. Of course, the t becomes a 1. The a is a constant, so we get an a. And the v naught is a constant, so it goes to 0. So as we can kind of see here, the second derivative did become the constant value we expected it to be. And essentially what we're going to do later on is actually take this formula and go backwards. So starting with this a here, we can actually go backwards to this quadratic. But once again, I don't want to talk about that quite yet. We'll actually be spending a significant amount of time talking about those kind of situations when we're going backwards. Now, what are s naught and v naught? Notice that when we plug 0 into our functions, those are the only terms that survive. So when we plug 0 into s, the only thing that's left is s naught. When we plug 0 into s prime, the only thing that's left is v naught. These are our initial distance and initial velocity. Basically, where does the object start? In this particular situation, since we're starting at the ground, and so we're starting at a height of 0, we're starting at s naught being 0. Then how fast is it moving when we do start? Well, we're assuming here they gave us the information that we're starting with a velocity of 144 feet per second. So v naught in this situation is 144. For what the acceleration is, we do need to go back to physics and realize that acceleration due to gravity is actually a known quantity. In fact, when we're talking about acceleration due to gravity, a lot of times they replace a with a g instead. And this has two values depending on the units you're using. If you're using meters, we do negative 9.8 meters per second squared. If we're using feet, we'd say it's minus 32 feet per second squared. Of course, here the negative is actually saying that we're accelerating downward. We're accelerating down towards the Earth. So we have to take that direction into account. I drew an arrow going up because we were talking about a positive 144 feet per second. We didn't throw the ball into the ground. We threw it upwards. And so we have a positive value. But the acceleration is downward, so we have a negative value. In this particular case, because we're using feet, we're going to use the negative 32. And so going back to our problem, part A, they want us to write the position, velocity, and acceleration functions for this ball. Of course, we basically wrote out our equation here. We've already determined that s naught is 0, v naught is 144, and a is negative 32. So we're just writing that out. Of course, negative 32 divided by 2 is a negative 16. And we're going to leave off the feet and seconds on this. So a quadratic with two terms, because the s naught was 0. Of course, they also wanted the velocity and acceleration functions. Of course, we can either just differentiate what we have here, or we can actually go ahead and use these equations up here, since we already have them written out. But it shouldn't be too hard to see that this is negative 32t plus 144, because that's what a is. A is negative 32. Or when you differentiate, we basically get a double the 16. The second derivative, of course, is a negative 32 that we expect the acceleration to be. In part B, they're actually asking, find the height, velocity, and acceleration at t equals 3. So after 3 seconds, 3 seconds after the ball has been launched, how high up is it, and how fast is it going? What is s of 3? Of course, we're just following our equation. We had negative 16. This was t squared. So t being 3, we get 3 squared. We have plus 144 times t, which is 3. And then plus 0, of course. Go ahead and use a calculator for that if you want, or you can work it out by hand. It's not too bad to do. We get 288. Of course, that is our distance function, and we're measuring our distances in feet. So since this is a numerical answer, we should give it its proper units. It's 288 feet. So it's 288 feet off the ground. If we look at the velocity of it, or s prime of 3, we have negative 32 times t, which is 3, plus 144. Again, work that out. We get 48. 48 what? Well, this is the velocity, is feet per second, are the units that we're using there. So it is actually still moving upwards. It's moving upwards at 48 feet per second. What is the acceleration? Well, our formula for acceleration was negative 32. It was just a constant. We don't even have to plug in 3. The units on acceleration are feet per second squared. Notice that every time we take a derivative, we end up with a over seconds that's added on there. Or I should say multiplied on there. So we divided by seconds once, then we divide by seconds again. Of course, that's because we're differentiating with respect to time. Basically, it's whatever units we had on our function divided by whatever units were on the variable that we're differentiating with respect to, which is usually going to be time. But of course, the acceleration is never changing. It's always the same. It's always the negative 32 feet per second squared. Part C, when is the ball at its highest point? So we know it's not at its highest point at 3. It's still going upwards. It's still getting higher. And then we want to know how high is this point? Well, how do we determine where the ball is at its highest? Basically, when does the ball start coming down? It just goes up, and then at some point it's slowed down enough that it's run out of upward velocity and it's starting to move downwards. At that point, its velocity becomes negative because it's moving downwards. So when it actually hits its peak, the velocity has to hit 0. It's slowing down as it gets up to the top, and then it becomes negative. So we're really asking, when is s prime, because we're looking at the velocity, when does the velocity hit 0? Of course, the velocity, we have the formula of negative 32t plus 144. And so we're solving for the t that makes this equal to 0. So move the negative 32t over, then divide everything by 32. 144 divided by 32 actually comes out to be a nice 4.5. I mean, there's a decimal, but at least it terminates pretty quickly. This is a numerical answer, so we should probably give it units. This is the units for time, and units for time we're using is seconds. So 44.5 seconds. So at 3 seconds, it definitely wasn't at its top, but a second and a half later, it does hit that top. Now they do want us to tell them how high is it at that point. All we have to do is plug in our value for t into our original distance function. So negative 16 times 4.5 squared, because that's our t squared. Then we have plus 144 times t, which is 4.5. Definitely want to think about using a calculator in this one. At least we're multiplying by things that have a lot of 2's in them, so the 0.5 will become an integer pretty quickly. But we get a nice round number of 324 feet. Again, feet because we're talking about distance in this problem. So it reaches a height of over 300 feet. Final question. How fast is the ball traveling when it hits the ground? How is the speed related to the initial velocity? So how do we know when the ball hit the ground? Well, the ground is at height 0. So we're really asking, when is the height equal to 0? Well, remember our height function was negative 16t squared plus 144t and then plus 0 because we had initial height of 0. We want to know when that equals 0. Of course, it is 0 when t equals 0. That's not a problem. When t equals 0, everything becomes 0. But that's where we started. We knew we started at the ground. What is the other solution to this equation? Well, if I'm looking for the other one, I'm not looking for t equals 0, so I can assume that t is not 0. I can just divide t out. Divide everything by t, and we get a nice simple equation of negative 16t plus 144 is equal to 0. It's actually very similar to what we had up here. We go ahead and move the 16t over to the other side. So we get 16t equals 144. And when we divide 144 by 16, we get 9. So after 9 seconds. So since I don't want to make another page, let's go ahead and let's move this over to the side. Because we have to solve one more last statement. But basically, it's going to hit the ground again after 9 seconds. 9 seconds after we launched it, at least. Now, that's not what they're actually asking. They're not asking when does it hit the ground. They're asking how fast does it hit the ground. So we're going to have to take this 9 seconds, and we're going to have to plug it into our velocity function. S prime of 9. Of course, S prime is negative 32t, which is 9, plus 144. And we get negative 144. Of course, this is a velocity, so it's feet per second. They're asking us, how is this speed related to the initial velocity? Remember that initial velocity was 144 feet per second. This velocity is negative 144 feet per second. Those look pretty similar. You only change the sign on it. It hit the ground at the same speed that it actually launched from the ground, but the direction is different. It's traveling downwards instead of upwards, so we change the sign. That's actually pretty standard for these kind of situations when we're talking about things that are being launched. Basically projectiles. When they're at the same height going up, they have the same velocity as when they're going down, except the sign is switched. They're going down instead of up now. But the point here is just we're using the second derivative. That's the whole point of this problem. And interpreting the second derivative as something that you've used before. Or at least we've gotten some idea before. You've definitely used the idea of acceleration at some point in your life. But there's not really too much more to say about the higher order derivatives. Like I said, we will use the second derivative again in Chapter 3. It will be used to solve some problems. The higher than that is not very commonly used, but they definitely do have some applications in certain contexts. But at this point, we just want you to know what they are. In our next section, we will move on to what we call implicit differentiation. it's kind of weird that was right in the middle, because what we're doing with implicit differentiation is going to actually involve the chain rule quite a bit, and it kind of, I don't know. I felt like this section was a little squeezed in a place that didn't make much sense. But it is kind of important that we have an idea of what this stuff kind of is, what the notations are for this kind of stuff, so we can actually use them later on. But for the moment, they're not really our main focus. So I'll see you guys in the next video where we'll actually get into that.